In this video we're going to start Chapter 5, and Chapter 5 deals with exponential and logarithmic functions. In Section 5.1 we're going to do the exponential functions, and then in 5.2 the logarithmic. And these two are actually inverses of each other. These are inverses. Like we have x squared and the square root of x are also inverse functions. Exponentials and logs in the same way are inverse functions. One undoes what the other does. And then in 5.3 we're going to look at some special properties of logarithms, and depending on, well, this year's been kind of weird, we might not have time to get to some of these logarithmic equations, and probably definitely not going to get to the logarithmic models. But where is this stuff important? Well, let's see. In mathematics, exponential functions involve a constant base and a variable exponent. The inverse of an exponential is logarithmic. Up until now, we've had stuff like x squared or x to the fifth, and it was always the base that was the variable. With the exponential functions, we're going to reverse that. We're going to have 2 to the x power, where the exponent is now the variable, or 5 to the x power. Where might this pop up in real life? Well, exponential and logarithmic functions are used widely in describing economic and physical phenomena, such as compound interest, population growth, memory retention, and decay of radioactive material. And there are careers out there. Maybe you're going to get a job in the future, and it's going to involve using some logs or exponential functions. Astronomers, psychologists, archaeologists, and forensic scientists are all careers that would use either one or both of exponential or logarithmic functions. So let's dive in. In Section 5.1, like I said before, we're going to cover exponential functions and their graphs. And what we're going to learn is to recognize and evaluate exponential functions with a given base a. A is just some number. We'll graph exponential functions using the one-to-one property. We will recognize, evaluate, and graph exponential functions with a base e. E is a special base, kind of like pi. Pi is 3.14, blah, 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 blah. E is also one of these special magic irrational numbers. And we're going to use exponential functions to model and solve some real-life type problems. So far, the text has dealt mainly with algebraic functions, which includes polynomials and rational functions. In this chapter, you're going to study two types of non-algebraic functions, exponentials and logarithmic functions. These functions are examples of, here's a new buzzword for us, the transcendental functions, the non-algebraic. And our official definition of an exponential function, the exponential function f with base a is denoted by f of x is equal to a raised to the x power. And remember, a is going to just be a number like 2, 3, 4, whatever. Now the variable is the exponent. And in this definition it says where a is greater than 0, a has to be positive, and it's not equal to 1. The exponent, x, can be any real number. And why did they say a does not equal 1? Well, the base a equals 1 is excluded because it yields f of x equals 1 to the x, that's just equal to 1. And this is a constant function, not an exponential. So first we're going to work on some calculator skills. Use a calculator to evaluate each function as at the indicated value of x. So here's our function, f of x is 2 to the x. We're going to evaluate that when x is negative 3.1. So that's what we're going to plug in for the exponent. And we're going to look at the next one, 2 to the negative x, when x is pi. And then 0.6 to the x when our x, or our exponent, is 3/2. So how do we punch this in the calculator? Well, the first one, we're taking 2 to the x and replacing that x with 3.1. So what we want is negative 3.1. We want to evaluate the base 2 raised to the negative 3.1 exponent. So on our TI-89 calculators, we're going to do 2 up caret for exponent, negative 3.1, hit enter, and we should get 0.1166291. For the next one, f of pi, this is 2 to the negative x, so we plug pi in for x and we get 2 to the negative pi. So the keystrokes are 2 up caret, negative pi, enter, and your display should read 0.1133147. And for the last one, it's 0.6 to the x power, so we're going to have 0.6 raised to the 3/2. So we have 0.6 up caret, and be careful now, we have grouping symbols around that exponent. Left parenthesis, 3 divided by 2 close parenthesis, then hit enter. Check the display so it looks like what you typed in. And your output should be 0.4647580. Let's check out some graphs of these exponential functions. The graphs of all exponential functions have similar characteristics, as shown in these next several examples. So in example 2, we're going to graph y equals a to the x for a couple different functions here. And we're going to sketch on the same coordinate plane, sketch the graph of each function. Well, all right, let's do them one at a time, and I'll do a little color coding on them. So let's make this a little bigger here. And we'll do blue for 2 to the x. So x is our variable, and let's start here at 0. When we plug 0 in for the exponent, 2 to the 0 has what value? Well, anything to the 0 power has an output of 1. For the next x input, 1, we're going to have 2 to the first power, or 2. And for the next x value, it would be 2 to the second power, 4. And let's go one more, third. 2 to the third power is 8. So we went from 0 up. Now let's see what happens when we go into the negative territory here. When we plug in x is -1, our function is going to be 2 to the -1 power. Remember, how to get rid of negative exponents is to move them to the denominator. So this is going to jump down and become 1 over 2 to the first, or 1/2. Well, what happens when we plug in a -2? Well, 2 to the -2 power, again, get rid of the negative exponent, move it to the base, or the denominator. So now we have 1 over 2 squared, and 2 squared is 4, 1/4. And the same thing for a third, or 3. If we make that 2 to the -3, that'll be 1 over 2 to the third, or 1/8. And if we look at this, is kind of symmetrical. Here we have 2, here we have 1 over 2. Here we have 4, here we have 1 over 4. Here we have 8, we have 1 over 8. And that revolves around, here our center line is sort of our x input of 0. 2 to the 0 power was 1. And then we're sort of just working on the left with fractions, on the right with whole numbers. So let's graph those points. 0, 1 goes right through the y-axis here at 1. And you're going to see, as we do more and more of these exponential functions, every exponential function crosses the y-axis at 1. Next point. 1, 2, over 1, up 2. Next point was x is 2, y is 4, so over 2, up 4. And the last one here on the positive side, over 3, up 8, so we would be well off the graph. Now let's go to the left of the y-axis. -1, our output is 1/2, so here at -1, we're going to go down to 1/2. At -2, we're down to 1/4. At -3, 1/8. You know, we could go all the way out to -1,000,000 and have, 1 over a very, very large number. But the idea is we're going to get closer and closer to that x-axis, but we're never going to touch it. There's always one more smaller fraction to the left. So we're going to approach but never touch the x-axis. So here's our function, 2 to the x power. Now let's work on the next one, was 4 to the x. Let's do that. Here, I'm going to change over to red. So if I plug in 0, 4 to the 0, or anything to the 0 is 1. Plug in x is 1, 4 to the first power is 4. Plug in x is 2, 4 to the second power is 16. Now let's work over here on the negative side. 4 to the -1 would be, move that to the denominator, 1 over 4, or 1/4. 2. 4 to the -2 is the same as 1 over 4 squared, or 1/16. If we did go one more here on the plus side, 3, 4 to the third is 64. And if we start to notice the pattern on our fractions, 4, 1/4. 16, 1/16. 64, this is going to be 1/64. And I'll change back to red to graph them. Again, the x-intercepts are the same. On the y-axis, we do hit at 1. But we go up sharper. Our next point is 1, 4. Over 1, up 4. Our next point is over 2, up 16. That would be about up here somewhere. So this graph is going much steeper, much faster. We cross at the same y coordinate. Ooh, I don't like that line too much. Here we go. Ooh, another terrible one. Now let's look into the fractions on the left here. -1, now we're down to 1/4. So we're under the 2 to the x function. At x is -2, now we're down to a 16th. So the red line here, this red exponential, is going to be under the blue one the whole way over. Again, they're both going to approach but never touch the x-axis. And this is 4 to the x. If I told you to graph 6 to the x, you could say roughly, well, it's going to cross at the same spot, but it's going to go, it's going to go up even steeper, and it's going to go down even lower on the other side. The bigger the base, the tighter to the y-axis you will be. You'll go up faster and faster. And let's see, I got a picture down here. This is probably the book's picture. Yeah, there we go. Let me just do this. So there's the graph, and of course you can see that the 4 to the x goes up much steeper, much quicker than the 2 to the x graph. They cross at the same y-intercept, and then they're both heading for the x-axis to the left as they head off toward negative infinity. An example 3, graph another one here. Now we're going to do negative exponents. So in the same coordinate plane, sketch the graph of each function. And let me make the graph a little bigger. There we go. So first, I'll go back to red here, is 2 to the negative x. So let's start here at 0 again. If I plug a 0 in for x, I get 2 to the 0. Anything to the 0 is 1. Now let's see what happens when I plug in the positive 1. 1 goes in there, so we get 2 to the -1, which is the same thing as 1 over 2 to the first, or a half. If I plug the 2 in for this x, I'm going to get 2 to the -2, or 1 over 2 squared, or a fourth. And if I plug the 3 in, 2 to the -3 would be 1 over 2 to the third, or an eighth. This is looking a lot like what we just did in the previous one, but now here, from 0 positive, we're getting fractions instead of bigger and bigger whole numbers. Let's see what happens when we head over here to the negative x values. If I plug a -1 in, let me erase a little bit of this. If we're plugging in now negative x values, I have 2 to the negative x, and if I plug in -1 for x, I get 2 to the negative first power, and that becomes 2 to the first, or just 2. If I plug x's -2 in, I get -2, and the negatives cancel, and I get 2 squared, or 4. And if we did go to -3, the negative -3 would be a positive 3, or 8. So let's graph it. Again, y-axis intercept at 1. And now, if we go to 1 on our x-axis, we're going to a y value of a half. If we go over 2, it's up a fourth. If we go over 3, it's up an eighth. So here, now to the right, we're getting closer and closer to the x-axis, but we're never going to touch it. And let's see what happens when we graph our negative x values. Well, if we go to x is -1, we go up to 2. If x is -2, we go up to 4. And then -3 would be up off the chart to 8. So we're headed up this way. This, when we graphed 2 to the positive x, this is 2 to the negative x. 2 to the positive x was just, a reflection about the y-axis. I took all the points on the left and moved them to the right, and that would be, our 2 to the x power, 2 to the positive x. Again, this is 2 to the positive x. The one we graphed here was 2 to the negative x. It's just a reflection about the y-axis. All right, let's check out the next one was 4 to the negative x. Oops. So now we're looking at 4 to the negative x. So we plug in 0, of course we get 1. All exponentials will cross there. Plug in a positive 1. 4 to the -1 is 1 over 4, or a fourth. Plug in a 2. 4 to the -2 is 1 over 4 squared, or a 16th. And 4 to the -3 would be 1 over 4 to the third, or 1/64th. And now to the negative numbers. 4 to the negative first power would be 4 to the first, or 4. plug in the negative 2. 4 to the negative 2 power is the same thing as 4 squared, or 16. So y-intercept is the same. Now if we go to negative 1, we're up to a positive 4 value. And negative 2 would take us well up off the graph to 16. So here's the start of our graph of 4 to the negative x. And as we head here to the right, we are going to be under that red line. We're dropping quicker toward the x-axis, but of course neither one will actually touch the x-axis. And here is the figure that came with the book. And there we go. See, 4 to the negative x, it's going up quicker to the left, and the 2 to the negative x is going up a little bit less steep. Again, these are both reflections about the y-axis. So if we compare the examples 2 and 3, we can observe that our original function was f of x was 2 to the negative x. That's the same thing as f of negative x. And the same for g of x. If g of x is 4 to the negative x, then that's the same thing as g to the negative x power. Consequently, the graph of f, capital F, is a reflection about the y-axis. The graphs of g and lowercase g have the same relationship. The graphs in figures 5.1 and 5.2 that we already looked at are typical of exponential functions, y equals a to the x or a to the negative x. They have one y-intercept and one horizontal asymptote, the x-axis, and they are continuous functions. The basic characteristics are summarized here. So if you have something as simple as some base to the x power, it has a domain. The x inputs are anywhere from negative to positive infinity. The range, the outputs are 0 to infinity. We're only going to have positive y values. We're never going to go below the x-axis. They have a y-intercept of 0, 1. The functions are always increasing. From left to right, they're always going uphill. The x-axis is a horizontal asymptote, and they are continuous. It just means there's no holes in them. We can draw the graph without lifting our pencil off the paper. If we have the function y equals a to the negative x and a is greater than 1, the domain is the same, negative to positive infinity. The range is the same, 0 to infinity, the positive y-axis. The y-intercept is exactly the same, 0, 1. Now the function is decreasing. As we look at the function left to right, we're always going downhill. We're sloping down. The x-axis is a horizontal asymptote. As our function heads towards 0, x approaches infinity. And again, this function is also continuous. Now in example 5, we're going to talk about some transformations of exponential functions. Each of the following graphs is a transformation of this basic function, 3 to the x power. Well, what if we add a number to the exponent? Up here we have 3 to the x. What if we happen to put a plus 1 up there? 3 to the x plus 1, or x plus 2. How does that affect the graph? Well, it's basically just a shift to the left. So here in the light gray is our 3 to the x power. If we do a 3 to the x plus 1 power, our exponents will just rise a little faster. Instead of this being 3 to the 0 and crossing at 1, it's going to be 3 to the 0 plus 1, or 3 to the first power, which is 3. So if you add numbers to the exponent, you're going to shift to the left. If we subtract numbers like x minus 1, it would be a shift to the right. We'd have this point, our y-intercept would be moved over 1, and our graph would just go up like this. So that's just a horizontal shift. Plus moves it to the left, minus moves it to the right. Okay, we had 3 to the x, and we messed around up here with the exponent, but what if we just do another whole number, 3 to the x minus 2? So this is a shift up or down. If it's a minus number, we're going to move the whole graph down that many units. If it was a plus, we'd move the whole graph up that many number of units. And if we look at the graph here, 3 to the x crosses at 0, 1, and it has the x-axis as an asymptote that it will approach but never touch. This minus 2 shifted everything down. So here we had our x-axis was our asymptote. Now this minus 2 tells us our asymptote has been shifted down. So this y equals negative 2 line is now our asymptote. Instead of crossing the y-axis at 1, we're going to cross 1 above our asymptote, which is now at negative 1. And our graph looks pretty much the same, just shifted down 2 units. Notice that the transformations in these figures, the previous one, 5, 7, and 5, 8, keep the x-axis as a horizontal asymptote. The transformation we just looked at yields a new horizontal asymptote of -2. Also be sure to note how the y-intercept is affected by the transformation. Again, this was a -2 transformation, so our y-intercept got moved down 1, 2 spaces. Our x-axis, our horizontal asymptote, got moved down 1, 2 units. Alright, what if we just put a negative in front of it? Here's 3 to the x is the upward sloping light gray graph here. Well, what happens if I put just a negative out front? Well, that sort of just reflects it about the x-axis. Here my intercept was at 0, 1. That got moved across the x-axis to 0, -1. Every point has just been reflected about the x-axis. So now instead of heading up toward infinity, we're now heading down toward -infinity. It was a reflection about the x-axis. And this we discussed in the first 2 examples. What if we have, here's 3 to the x, again, the light gray graph sloping up. What if I wrote 3 to the -x? Well, that's just another reflection about the y-axis. Now the y-intercept stays the same, but now instead of heading up toward infinity, we're sort of heading down toward 0, our asymptote. Alright, a couple practice problems to try. The first, to evaluate the function to the indicated value of x, round to 3 decimal places. In the next one, it says use a graphing utility to construct a table of values for the function. So get out the TI-89s, TI-89 calculators, and we're going to make just a table for this for a few x values. And we're going to see what that 2 to the x minus 1 power does. So pause the video, try the practice problems, and then start it back up and see how you did. Okay, let's see the first couple here, just calculator problems. If you punched it in right, you would have done 0.9, up caret 1.4, enter, and you should have got, and let's see here, 0.862858, and they wanted it rounded to 3 decimal places, so that would have been 0.863. The next one was 5 to the x, and we wanted to plug in -pi, so it'd be 5, up caret, the negative key, pi, enter, and you should have got 0.006. Alright, let's look at this one we're going to graph now. And it said to do the table on the calculator. I'll do a quick table without it, because who needs a calculator in math class? I always like to start these at 0. So we got 2 to the x minus 1. Well, if I plug 0 in, 2 to the 0 minus 1 is 2 to the -1, or 1 over 2, 1/2. And let's do it as a decimal. And now I plug in this x is 1. 2 to the 1 minus 1 power. Well, 1 minus 1 is 0. 2 to the 0, or anything to the 0, is 1. And now I plug in a 2. 2 minus 1 is 1, so 2 to the first power is 2. If I plug in the 3, 3 minus 1 is 2. 2 to the second power is 4. Plug in the 4. 4 minus 1 is 3. 2 to the third is 8. And now let's do some of these negatives. So I'm going to do 2 to the -1 minus 1, which is -2. 2 to the -2 power is 1 over 2 squared, or 1/4. And we'll do that as decimal 0.25. And if we plug the -2 in, -2 minus 1 is -3, so 2 to the -3 is 1 over 2 to the third, or 1/8, or 0.125. And now the last one, -3, that is 0.0625. Well, let's graph it. At 0, we go up to 0.5, so there's our y-intercept. 1, 1 is our next point, over 1, up 1. And then 2, 2, over 2, up 2. And then 3, 4, over 3, up 4. And then over 4, up 8. That's definitely off the graph, maybe up around here somewhere. As we go to the left, -1, our value is 0.25. And at -2, it's 0.125. And then it gets even closer as we move to the left. So our graph is going to look something like this. There we go. That is 2 to the x minus 1 power. For the homework for this stuff, page 398. Numbers 7 to 10 are matching problems. 11 to 14, you're just describing the shift. Is it a shift left or right, up, down, reflected, about the axis, x-axis, y-axis? So for 11 to 14, when you're describing the shift, you're going to be looking back to these examples here. What is that? Example 5, A, B, C, and D. Enjoy the homework.